Right now, we're going to be talking about Ohm's law and how it applies to energy in an electrical circuit. So let's start with the statement of Ohm's law. Ohm's law simply states that the voltage is equal to the current across a resistor times the resistance of that resistor. Now, in here, V is going to be standing for the voltage. Now, if you're talking about the total um, for this entire system, the voltage you're talking about is the battery voltage. But if you're looking at an individual resistor, just one within the group, the the voltage that you get is going to be just for that single resistor. I continues to stand for current, which is in amperes, and R stands for resistance in ohms. Power. Remember, we're going to be converting electric potential energy, that stored energy, that voltage, into electrical energy, as in the current flowing. So, power, just remember, is that energy over time. We talked about that earlier in the work, energy, and power unit. And when it comes to electrical energy, power is simply the current across or the current through a resistor or through a circuit times the voltage across that resistor or across that circuit. So P is power. Its units are watts, which are joules per second, a volt, um, which is the joule per charge or energy per second, and I current, which is in amperes or charge per time. Okay. So those are just our quick reminders of what everything on this means. Now, in applying these, we're going to need to go back to using a circuit diagram, and we're going to have a specific value here that our battery is 3.2 volts. I'm asking you to copy the questions in the diagram right now. Seriously, pause and do that. Cool, you're back. So, how are we going to do this? What we're going to do is actually look for what we're going to actually, this is one of those times we're combining our resistors. So, starting with our two sets of resistors that are in both in parallel with each other. And when they're in parallel, they're going to, remember, be 1 over R1 plus 1 over R2. In this case, I'm just calling it R23. And we can get that for the 5 and 6, we can get that. And if you notice, we now have all of those in series, which allows us to redraw this as here, add up all the resistors, and get our equivalent resistance. So now that we found the equivalent resistance, we're going to need to find the current through this. So the V equals IR, and I is equal to V over R. Do a quick rearrangement. So that means the current is the voltage, 3.2, divided by that equivalent resistance that we just found, meaning our current is 8.17 milliamps. And finally, we need to find the power. To find the power, this is a really quick and easy thing to do. We just use our power as IV, plug in the appropriate numbers, and punch in our calculator to get that it's 0.0261 watts.